Initial coordinates locked.
Welcome to Ultimate Megaprojects.
Hey, I'm Jack Hyber, and today we're taking a deep look at the Gordie Howe International Bridge, named after the hockey legend who was born right here in the shadow of this river and who played on both sides of the border his entire career.
What you just watched is not a demolition. That is the moment China declared war on an entire mountain range. To build a single airport, Chinese engineers didn't find flatland. There was no flatland. So they made a decision that sounds completely, utterly insane. They would destroy 400 mountains. $123 million, 6 years, 2,000 workers, 800 machines, and one of the most audacious engineering projects in the history of human aviation. An airport on top of a cliff at 5,810 feet above sea level, higher than most aircraft cruise over Europe. Pilots call it the aircraft carrier in the clouds, and the story of how it was built will change how you think about what is possible. We're going to break down exactly how Chinese engineers flattened an entire mountain peak, filled surrounding valleys with hundreds of millions of tons of blasted rock, and built a fully operational international airport runway at 1,771 meters, 5,810 feet above sea level. We'll cover the controlled blasting operations that shattered solid granite mountains, the cut and fill engineering strategy that turned jagged peaks into flat ground, the insane runway construction challenges at high altitude, and the secrets, the delays, the geological nightmares, and the one engineering problem that nearly stopped the entire project. This is not just a construction story. It is a story about what happens when a nation simply refuses to accept that geography is an obstacle. Let's get into it.
This feat of innovation connects remote areas overcoming extreme to the details.
You need to understand where it is. Wulong County, deep in the mountainous interior of Chongqing Municipality, one of China's most densely populated and economically important regions. The three gorges of the Yangtze River cut through this landscape, dramatic, breathtaking, and completely inaccessible by conventional transport. For decades, the communities of Wulong and Fengdu, home to hundreds of thousands of people, were effectively cut off from China's rapidly modernizing economy. The nearest major airport was hours away on roads that wound through mountain passes. Getting to Chongqing City meant a journey that could take an entire day. And here's the economic reality. This region is sitting on a gold mine of tourism potential. The karst limestone landscapes of Wulong are UNESCO recognized. The Three Gorges are one of China's most iconic natural wonders. Millions of tourists want to come here, but without air access, the economic engine simply cannot start. China's solution, as it so often is, was not to work around the geography. It was to eliminate it. Cut to initial survey footage. Engineers on mountain peak measuring, planning. In 2009, Chinese aviation authorities began feasibility studies for a new airport serving Wulong and Fengdu. The surveys confirmed what everyone already knew. There was no flat land. Not a single site within reasonable distance of either city offered anything resembling a viable airport location, except one possibility. Show Tawa Mountain aerial. Tawa Mountain, 1,800 meters high, a jagged peak above the clouds, completely unbuildable by any conventional definition, unless you were willing to do something no airport engineer had ever seriously attempted at this scale. Cut the top off the mountain entirely, fill the surrounding valleys with the rubble, and build your runway on the newly created plateau hovering above the clouds. Beat. The proposal was approved in 2013. Construction began April 2015. The impossible was officially underway. Not all of it, but enough. Engineers calculated that to create a runway plateau of sufficient size, they needed to remove the top 29 meters of Tawa Mountain's peak and redistribute hundreds of millions of cubic meters of rock into the surrounding valleys that flanked it. The math was staggering. The total Earth movement required for this project exceeded 55 million cubic meters, enough material to fill 22,000 Olympic swimming pools, moved entirely by machines and men in mountainous terrain at nearly 6,000 feet of altitude. But before the machines could work, the rock had to be broken. And Tawa Mountain's rock was not cooperative. Large sections of the peak were solid granite, one of the hardest naturally occurring materials on Earth. Conventional excavation equipment simply could not cut it. The only answer was controlled explosive demolition, and lots of it. Engineering teams drilled precise patterns of blast holes into the granite face, each hole bored to an exact depth and angle, loaded with carefully calculated charges. The blast sequence was designed not just to shatter rock, but to direct the energy of the explosion to fracture the mountain along predetermined planes, breaking it into pieces that excavators could actually handle. The first major blast in April 2015 shattered millions of cubic meters of rock in seconds. The sound was heard for miles, and as the dust settled, the machines moved in. Over 800 pieces of heavy equipment, excavators, bulldozers, dump trucks, compaction rollers, descended on the site simultaneously. From above, they looked like insects attacking a giant, but there were so many of them working so continuously that the mountain began to visibly change week by week, month by month. 2,000 workers operating in rotating shifts, 24 hours a day, 7 days a week. Because at this altitude, every season brings new challenges, and the weather window for optimal construction is narrow. The engineering strategy driving this entire project has a deceptively simple name: cut and fill. Think of it like this. You have a mountain peak that's too high and valleys on either side that are too low. You take material from the peak and use it to fill the valleys, creating a flat, level platform in between. The mountain itself provides its own fill material. No need to import billions of tons of rock from elsewhere. In theory, elegant. In practice, an absolute engineering nightmare. The problem is stability. Freshly blasted rock dumped into a valley is not solid ground. It's a loose pile of irregular fragments with air gaps, water infiltration, and no structural integrity whatsoever. If you built a runway on that, it would crack, settle, and collapse within months. The solution was dynamic compaction. Essentially, a crane drops an enormous steel weight, sometimes weighing hundreds of tons, repeatedly onto the fill surface from a significant height. The impact sends shockwaves through the loose fill, forcing the fragments to settle tightly together, eliminating air gaps, and dramatically increasing the load-bearing density of the ground. This process was repeated systematically across every section of the filled valleys. Thousands of drop impacts, monitored by sensors, until the ground met the precise engineering specification required to support the weight of a fully loaded commercial aircraft. And then there was water. At 1,771 meters altitude, rain is not gentle. Heavy rainfall events could dump enormous volumes of water onto the construction site, turning the blasted rock fill into a slurry that could trigger landslides down the mountain face. Engineers had to design and install a comprehensive drainage network before and during filling operations. Channels cut into the bedrock to capture and redirect water away from the fill zones, preventing saturation of the newly placed material.
Unstable rock and compaction
Every meter of
issues.
elevation change across the entire
nightmare.
plateau had to be calculated and verified to tolerances of centimeters. Because a runway that isn't perfectly flat doesn't just inconvenience passengers, it makes aircraft landing genuinely dangerous. With the plateau established and the ground compacted to specification, the real construction began. A 2,600-meter runway, That's 1.6 miles of precision-engineered pavement, built to international aviation standards at nearly 6,000 feet above sea level, in conditions that would challenge construction operations anywhere on Earth. A commercial runway is not just pavement. It is a precisely engineered layer cake designed to distribute the enormous concentrated loads of aircraft landing gear across the subbase below without cracking or deforming. From bottom to top, compacted subbase, then layers of crushed aggregate stone, each compacted to exact density specifications, then asphalt base course, asphalt binder layer, and finally the surface asphalt, a specialized high-altitude mix formulated to resist the freeze-thaw cycles of mountain winters, where temperatures can drop to -15 degrees Celsius or 5 degrees Fahrenheit, and ice formation in the pavement surface is a constant threat. Asphalt paving operation at Wulong required extraordinary precision. Asphalt must be laid and compacted while it is still hot. The temperature window for proper compaction is narrow, and at high altitude, the asphalt cools faster than at sea level. Paving teams worked in carefully choreographed echelon formations, one paver immediately behind another, to ensure no cold joints formed in the surface. A cold joint is a weakness in the pavement structure. On a runway absorbing the impact of a 70-ton aircraft landing at 140 miles per hour, weakness is not acceptable. For the parking apron, where aircraft sit stationary under their own weight for extended periods, asphalt was not sufficient. Engineers used reinforced concrete slabs, thick, dense, and capable of supporting the static load of multiple parked jet aircraft simultaneously without deforming. And here is the detail that makes this runway truly unlike any other on Earth. At the end of the runway, there is no flat ground, no runway safety area extending into fields. The plateau simply ends, and beyond the end, a cliff drops hundreds of meters into the valley below. Pilots approaching Wulong Airport must touch down within precise distance limits on the runway surface because there is no room for error. Overrun the runway, and the aircraft goes over the cliff. That is not a metaphor. That is the literal operational reality of the aircraft carrier in the clouds. Navigation and landing systems. Thousands of runway edge lights, each one individually calibrated and tested, line the runway to guide pilots through the mountain fog that regularly reduces visibility to near zero. The instrument landing system, the electronic guidance beam that allows pilots to land in zero visibility conditions, was installed at both runway ends and calibrated to Aviation Authority standards with extraordinary precision. At Wulong, these systems are not backup equipment. They are the primary way most aircraft approach and land. Weather monitoring. Mountain weather is unpredictable in ways that coastal and lowland airports never experience. Wind shear, sudden violent changes in wind speed and direction, is a particular hazard in mountain terrain. Wulong Airport's weather monitoring network includes anemometers, visibility sensors, and wind shear detection equipment positioned around the entire airport perimeter, feeding real-time data to the control tower. The terminal building. While the runway was being completed, the terminal building was rising from the concrete plateau alongside it. The design, deliberately echoing the surrounding mountain peaks in its roofline, houses a 3,500 square meter passenger hall with glass walls offering panoramic views of the karst landscape below. Inside, baggage handling systems, check-in counters, security screening, and a cargo handling facility capable of processing 1,200 tons of cargo annually were fitted out and tested. The control tower, rising above the terminal building, gives air traffic controllers direct line of sight coverage of the entire runway and approach paths. In mountain terrain where radar coverage has gaps and radio communication can be affected by terrain masking, that direct visual line of sight is critical to safe operation.
This has been Ultimate Mega Projects. If this video blew your mind, hit subscribe, because next day we're going inside an even more insane engineering project that nobody is talking about yet.
So why does a $123 million airport on a mountain in China matter to the broader world? Because it is the most vivid demonstration of a strategy China has been executing quietly, systematically, and at extraordinary scale for 2 decades. China has built over 260 commercial airports since 2000, more than any other nation on Earth, more than the entire European Union combined. And a significant proportion of those airports are not in flat, convenient locations. They are in remote, mountainous, geologically challenging terrain, serving communities that would otherwise remain economically isolated. The economic impact of Wulong Airport is measurable and significant. Before the airport opened in 2019, annual tourist arrivals in Wulong County were limited by access. Within its first full year of operation, the airport was handling flights to major Chinese cities, including Chongqing, Beijing, and Shanghai. Tourism revenue in the region increased dramatically. Local businesses, hotels, restaurants, tour operators saw demand surge. For the United Kingdom, US, and international tourists, the opening of Wulong Airport made one of China's most spectacular natural landscapes genuinely accessible. The UNESCO karst formations, the ancient landscapes of the Three Gorges, the cultural heritage of communities that had been effectively cut off from international tourism, now reachable within hours from any major hub. And for China itself, this airport is a statement, a demonstration that no geography is too challenging, no terrain too hostile, no mountain too high to prevent the integration of its most remote communities into the national economy. Now, let's talk about what the official project narrative doesn't emphasize: the timeline nightmare. The project was originally scheduled for completion in 2017. It opened in August 2019, a 2-year delay on a 6-year construction project. The official explanation cited weather delays and geological challenges. What the official narrative glosses over is that solid granite sections of Tawa Mountain proved significantly harder and more expensive to blast and remove than the initial geological surveys predicted. Equipment breakdowns in high-altitude conditions, where thinner air reduces engine efficiency and extreme temperature cycling stresses mechanical components, contributed to the timeline slippage. The environmental cost. Destroying 400 mountains, or more accurately, dramatically reshaping 400 mountain features across the project area, has an environmental cost that is rarely discussed in the engineering literature. The karst limestone ecosystem of Wulong is extraordinarily sensitive. Karst landscapes are riddled with underground cave systems and aquifer networks, water systems that local communities and ecosystems depend on. The blasting and fill operations permanently altered the underground hydrology of the project area. Local farmers reported changes to spring water sources. Cave systems that had existed for millennia were sealed by fill material. The safety margins. Show runway and cliff footage. The operational safety margins at Wulong Airport are tighter than at virtually any other commercial airport in China. The runway length of 2,600 meters, while sufficient for the regional jets that serve Wulong, leaves limited margin for emergency overrun. The runway end safety area, the flat ground beyond the runway end where an aircraft that can't stop in time can safely decelerate, at Wulong is significantly shorter than international standards recommend for an unrestricted airport. The cliff at the runway end is not just dramatic, it is a genuine operational constraint that limits which aircraft types can safely use the airport. Behind every machine and every cubic meter of blasted rock in this story, there are human beings. There are the 2,000 construction workers, many of them from rural communities across Chongqing municipality, who spent 6 years on top of a mountain, working in summer heat that baked the rock face to temperatures that could burn through work gloves, working in winter cold that froze equipment hydraulics and turned the construction site into a sheet of ice, working through mountain fog so thick that visibility dropped to meters, far from their families, living in basic site accommodation on a plateau that didn't yet exist when they arrived. There are the local communities of Wulong and Fengdu, farmers, shopkeepers, tourism workers who watched the mountain above their valleys slowly transform over 6 years, wondering if the promised airport would ever actually appear, and who on August 16, 2019, watched the first commercial aircraft touch down on what used to be a mountain peak and felt their world genuinely change.
What you're about to see
And
is
there are
not
the
a
pilots
metaphor.
who fly into
This is a literal
Wulong,
reality.
who approach through mountain
aircraft
fog,
carrier in
following
the clouds,
instrument guidance
and
to
it's
a
landing
runway
right
that
now.
ends at a cliff edge, who call it the aircraft carrier in the clouds because landing there requires the same precision, the same commitment, the same absolute professionalism as landing a jet on a moving ship at sea. Every megaproject has a human story. This one's human story is about people who refuse to be left behind by geography.
So here's where we land. The Chongqing Wulong Airport is simultaneously a $123 million feat of engineering that defies rational explanation and a perfectly logical response to the challenge of connecting remote communities to a modern economy. China destroyed 400 mountains, moved 55 million cubic meters of rock, spent 6 years building a plateau where none existed, and created an airport that operates at nearly 6,000 feet above sea level on the edge of a cliff in one of the most geologically challenging environments on Earth. And it works. Every day, aircraft land and take off from a mountaintop. Tourists arrive from Shanghai and Beijing to see landscapes that were effectively inaccessible a decade ago. Local economies that were stagnating are growing. So, I'll leave you with this question. Is the Chongqing Wulong Airport the ultimate proof that human engineering can conquer any geography, that no mountain is too high, no terrain too hostile, no challenge too impossible? Or does the environmental cost, the compressed safety margins, and the
Now,
2-year
the
delay
truth,
tell a more complicated
they don't
story
tell you.
about what we lose when
Timeline
we
delays
decide
are
that
mounting.
nature is simply an
These
obstacle
safety
to be
margins are
removed?
vanishing.
A mountain that stood for
The
millions of
original
years,
plan, completion
gone
in
in 6.
2017.
Was it worth
The
it?
reality, August
If this
2019.
breakdown changed how you
A
see what's
2-year
possible in
delay.
engineering,
What hard in
hit that
geology.
like button.
This has been Ultimate Mega Projects. If this video blew your mind, hit subscribe because next day we're going inside an even more insane engineering project that nobody is talking about yet.
Every frame in this video has been crafted through a multi-stage documentary production process, from original research and script development to AI cinematic visualization and professional editing. Human creativity guides every step. A digital documentary host and advanced visual tools are used to clearly explain complex mega projects, engineering, and global infrastructure. This channel is dedicated to original documentary storytelling and follows all YouTube policies regarding AI assisted and synthetic media, ensuring the informative, unique, and monetization